topology they have and how that plays with numerical invariance of objects. So in particular, don't get too excited, the numerical invariant I'm thinking of is the degree of a polynomial. So the outline of this is we're going to see something called the upper naturals. We're going to then define the algebra of polynomials in 3 different ways and prove two things. By a few, I mean very few. And then we're going to see that crisp things have natural number degree. So a basic sort of slogan or idea to keep in mind is that the spacier your domain of discourse is, the more its native logic is constructive or intuitionistic. In other words, it violates classical principles such as the law of excluded middle or the axiom of choice or either thing. And there's a ton of really interesting work in this area. In particular, Martin S. Cardo does a lot of really interesting synthetic topology just from the constructive, computable nature of data types. But this also comes up even if you're just a sort of mathematician who's not interested in computability, because if you work inside certain categories where the objects have some kind of cohesion or some kind of variation, so for example, in certain categories of sheaves that we've been seeing earlier in the week, then the logic in there will not satisfy the constructive, the classical principles that you might assume about the category of sets. So, in particular, I used this in my last talk, but I would like to mention it again. A proposition is logically connected if, whenever it is universally contained in a disjoint union, so a disjunction, where two propositions that contradict each other, then it's either universally in the left half or universally in the right half. So you might think another way to say this is if you put something connected in and you take some proposition about it that must either be true or be false, then it must be true everywhere or false everywhere. And so 2 quick lemmas here. First, if we have a logically connected proposition, then its image under any map is logically connected. And this follows very sort of straightforwardly from the adjunction you get. And that lets you bounce things back to where you know something about you. And finally, if a type has decidable equality, you need to decide whether any two things are either equal or not, then logically connected propositions have at most one element. And this is very easy to see because we have that U of A, let's say, implies, so here we're gonna go here, A equals B, or not A equals B. That's because we've assumed equality to be decidable. Yes?
What setting are we working in?
Oh, we're in type theory, and not type theory. Or in the internal logic of equivalence. So this is, okay, it doesn't, if you, formally I'm working in type theory, and formally I would be working in a constructive setting. So we have this. This now is true. So that's why we have this map here. And therefore, since this is connected, we have this for all A. We have that UA implies A equals B, or UA implies not A equals B. And for a free B. So if there is a B that satisfies U, then it must be the top one. Because if it were the bottom one, we'd get a contradiction, because B equals B. So suppose R is a ring. Naively, we would think that taking the degree of a polynomial is a map from polynomials for R into the natural numbers. Now, suppose R is logically connected. If we have an element of R, we can form the polynomial Rx. And therefore, the degree of Rx is a natural number. So we can abstract R to get a function from R to the natural numbers. But R is connected. So the image of this function is also connected. But the natural numbers have decidable equality. So this function is constant. And therefore, the degree of x, which is 1, must equal the degree of 0, which is 0, which is a minor issue. So we might want to fix this. Now, before we go and fix it, I want to tell you that this actually happens. So, in particular, so in real cohesion, R, the Dedekind reals, is connected. And the reason it is connected is if we have, suppose we have P R the prop such that for all R in R, PR or not PR. Then we can define a map. Then let R bool, I'll call PR, be the map sending R maps to true if PR, and false if not PR. Now, yes?
I'm having trouble understanding what it means for a ring to be logically connected. I thought you defined that for propositional functions.
I'm sorry, yes. A type is connected if the constant true proposition, which represents the whole type, is logically connected as a proposition in this way. So what that amounts to is that if you have a type that's connected, if any decidable predicate upon it is either uniformly true or uniformly false. So we give a map here into bool.
Sorry,
Yes.
What is the method you institute to any type? Except if you have any type, you can also get in such a kind of position.
Just constantly true.
Oh, constantly true, yes. I'll write this.
Yep.
So for a type A to be logically connected, that means that lambda A dot true, which goes from A to prop, is logically connected. So it's the constant function at true. And if you expand what this looks like here, we have that true A, it's true of anything, implies P or A or not PA, right? That's just saying that for all A, PA or not PA.
You think you can define it the other way around too? First, define a logically connected type, and then say a prop is logically connected if it's.
Yes, you can, and they're equivalent. So this is equivalent to the definition where you define just what it means to be a logically connected type, and then you apply it to a subtype by taking the dependent sum. Yes.
I think if we have a topos, then the type being connected to it is just the classical notion that it's not a coproduct.
Yes. Thank you. That's a great
It's
point.
the same thing.
So the type is connected when it's not a coproduct, but this is a positive way of saying this, which is if we did have a decidable proposition on it, where it wasn't uniformly true or uniformly false, then you would have a coproduct where you have the part on which it's true and the part on which it's false, and they are disjoint. And if that was true everywhere, then that would be the whole type, and so it would be a disjoint union. And you can prove that in the type theory that this is the resulting notion here, that you do get that. Although saying not disconnected in this way would be a somewhat a double negation. So this is the same as saying same as for all A, PA or not PA implies for all A, PA or for all A, not PA. Freshman's dream, right? Love it. So, okay, so as a reminder, if we had a ring like this, then we can't take degrees valued in the natural numbers. And I want to tell you that you do have a ring like this. In particular, if we go back, if we take real cohesion, we're working with R. Now, this has a special property. The special property is that a type is discrete if and only if every map from R to it is constant. Now, without going into much particular, bool is provably discrete. It is effectively a fact that if you take an inductive definition, you don't throw any extra variables into it, it ends up being discrete. So this has to be constant, which means that this proposition has to be uniformly true or uniformly false. So in this setting, we do have a ring. It's the real numbers. That's a very important fact. So already in real cohesion, we can't be taking degrees in that way. And I'll note that if you were working in, say, Zariski topos, in Zariski topos over S, where S is connected, and then the affine line for S is logically connected. And you can give an internal argument for this too in a setting that I don't want to go into right now. So, okay.
It follows from synthetic.
Yes, it does. It follows from synthetic question.
From what?
It's the abstract setting in which you can prove this also internally. So you can prove, we've proven that the reals are logically connected internally, assuming something about our type theory, and assuming something else, you can prove that the affine line is.
And basically because at least in three-shift topos is representables are connected.
Yeah.
And then you have to see why it's also in shift topos.
Yes. Yeah. All right. So so there's a little problem with the naturals. They're a bit too discrete for us. How can we fix this? We'll fix it by finding another problem from logic and fixing that. So our problem is this. The law of excludability is equivalent to the well-ordering principle for the natural numbers. And here's how that goes. So I'll assume, yes.
Yeah, sorry, I asked something. So in worse, what you've argued, or this condition you've shown says that if you do regard polynomials over real numbers as being a continuous space, there's no continuous degree because they're always continuously move to zero, but the degree switches.
Exactly.
And also, that's not what anybody usually does. One would take real discrete object to reason about the polynomial ring. So usually we wouldn't want to fix this by changing the natural number. We'll just say let's consider the polynomial ring not as a continuous object. Why?
No, you wouldn't.
Well, then you have so for example, especially in the algebraic domain, you really want to have this because it lets you do the internally to the Zariski topos say you have the unity of algebra and geometry that algebraic geometry promises. In that case, the polynomial algebra over the affine line is actually just functions from the affine line itself. And so in you would want to also use these continuous polynomials if, say, you want to continuously parameterize a polynomial for some reason, ever. And if you just only did your theory for discrete polynomials, then you can never have them varying continuously over something that itself is connected. So you'd be restricting your theory all the way back to something discrete, and then you lose this nice setting that we have where everything has an innate topology. So the the law of excluded middle is equivalent to well ordering. I'm going to assume you know how to prove the well ordering principle, and we'll do the other way around. So we can show that the well ordering of the natural numbers implies the law of excluded middle. So given a proposition, define this proposition P bar by P or 1 is less than your number. So your number is bigger than 1 or P. And note that if you plug in 0 to this, it reduces just to P. In fact, 0 is the least number satisfying this proposition, if and only if this proposition is true. And 1 always satisfies this proposition. So the least number has to come from 0 or 1. And therefore, the proposition has to be true or false, because equality of natural numbers is decidable. So we have another problem about natural numbers coming from logic in this setting, which is that if we don't assume a universal classical axioms, which, as I was describing, breaks your universal notions of continuity, that every function is continuous in some sense, then you don't have the well ordering principle, which means it's kind of hard to make definitions of the form, well, the degree of a polynomial is the least number after which all its coefficients are 0. That's not a number. What is it? Well, one way to see this as category theorists is that the natural numbers are not complete as a prop-enriched category. So the natural numbers have an ordering. That ordering lands in prop. It also happens to be decidable, so it lands in bool. You can consider it as a bool-enriched category. But it turns out that decidable propositions are well ordered in this sense, because you have your normal sort of intuitive algorithm, which is you run up the natural numbers checking your proposition. But that only works if you can actually check on each natural number whether it is true or it is false. So we don't have that. So we can just complete it. We're going to take the Yoneda perspective. We're going to consider every number to be its upper bounds. So we define a number by what bounds it from above. And as a category, this will be the upcoprecious. So the completion category, the enriched category. More prosaically, the upper naturals will be the type of upward closed propositions on the naturals. So first thing I would like to compare this to is the notion of a Dedekind cut. This is something like a Dedekind cut on the natural numbers, on the rational numbers. And it's sort of well known in constructive analysis that Dedekind cuts, upward Dedekind cuts, downward Dedekind cuts, and two-sided Dedekind cuts are different things on the naturals. I mean, on the rationals. They give you different real numbers, if you will. And here you do get different naturals if you do upper and lower. And if you do two-sided, you can prove that that's the natural numbers. So, yes.
Just remarks of should I think of this completion as pre-shapes, but then not for the set, but the one level lower, namely the 0 levels of prop. Yes,
You can think of it this way.
So would this be able to
Yes. Yeah. We can think of an upper natural as defined by its upper bound. So the proposition holds of a natural, the upward closed proposition holds of a natural. If that natural is an upper bound of the proposition, this way, I'm going to stop saying proposition, I'm just going to call them upper naturals. And we can define an ordering where we say that n is less than n if every upper bound of n is an upper bound of n. And there's that off. Okay. So from every natural number, it has its predicate of being an upper bound, and that defines an upper natural. This gives us a sort of Yoneda embedding. This is just the Yoneda embedding. In fact, everything I will do for the next few slides is just the notions you know and love from pre-sheets, if you do know and love them. And we'll define infinity to be the upper natural with no upper bounds. It's always false that a number bounds it. Okay? And we say an upper natural is bounded if there merely exists an upper bound for it. You could also say it's finite. And now we've solved the problem, because we can take the minimum upper natural satisfying a predicate on natural. And you can also take the minimum upper natural satisfying a predicate on upper naturals if you can resize proposition. So how does this work? Well, it's just going to be, what does it mean to the upper bound a predicate on naturals? It means that you are above something that satisfies that predicate. That's what that definition there says. So we can prove a little lemma, which is very nice, which is that the minimum is a bona fide natural if and only if that natural is actually the minimum. It's good, sanity check. And a lot of these will work is that we've sort of expanded our notion of natural number, but if we check it on naturals, everything's back where we were. And we can define the arithmetic operations for upper naturals by deconvolution. So this is the normal deconvolution formula, but here's another way to say it. N is an upper bound of the sum if there exists upper bounds A and B of N and M respectively, and N is an upper bound of the sum of those things. And similarly for multiplication. And now I won't go into it, but because these are deconvolutions, and by sort of abstract nonsense, by which I mean actually you just have to calculate it, these will satisfy, these will form a ring on this, not a ring, center. So a word on what it looks like in models. I'm going to tell you about localic models because it's fairly intuitive. So these are like sheaves on a space. It's going to be the sheaf of upper semi-continuous functions on the naturals. And this ties into what I said. If you take lower cuts, you get lower semi-continuous functions. If you take two-sided cuts, well, that's the order topology on the naturals, which is discrete, and that's why you get the natural cuts. So in particular, here's an example from Hartshorne. If Y is a Noetherian scheme, F is a coherent sheaf on it, then this gives you the definition of the dimension. Write this one down because I'm going to mention it later. Not sure. So this is an upper semi-continuous function. It's a pretty straightforward exercise. And therefore, it's a global section of the upper naturals. And that's the idea here, is that when we do things internally, they're going to end up being upper naturals because externally they're upper semi-continuous functions. And for more upper naturals in the localic setting, Ingo Blechman has in his thesis a section on them that's quite nice. So I should mention about upper naturals. So they're not my notion in any way. I have no idea who invented them. I consider this to be folklore, but I would love to be told otherwise. So I learned about them from the categories mailing list and an offhand comment by Levere. If anyone has a better origin. Okay, so one thing we can do that we couldn't do before is we can define the cardinality of a type. And so the cardinality of a type, now this is actually going to be a function from types to upper naturals, which is nice. And it's just defined to be the minimum number, n, such that the finite set on n elements is equivalent to a type. And we could also do the Kuratowski cardinality if you wanted. And I'm very interested in what it means to do everything in algebra with Kuratowski cardinality instead of regular cardinality, so if you know, please tell me. And we have a few propositions. Product goes to product, sum goes to sum, and we have an exclusion. The asterisk there is to remind me to tell you this. We need these to be embeddings. This. And the other thing the asterisk is there to remind you is that minus sign is defined just analogously to plus. However, it is not exactly an inverse of plus. And it's a truncated minus, first of all, but it also just, it doesn't quite, one of the directions will get you back where you're going, but the other one doesn't. So it doesn't sort of commute with addition. And that's a feature of the one-sided nature of the class. So, okay. So now I'm going to tell you about polynomials 3 ways so I can define the degree. So the first way, maybe the most naive way, is we're going to say that a polynomial is a free R algebra. So we can define the free R algebras by just throwing them in. This is the beauty of higher inductive types. So what we do is, given a type I of indices, we will define the free R algebra on I to be, it has a function which we call x from I into R, the free algebra. And then it has an R algebra structure, which is my way of not writing out a gazillion things on this slide. So what I mean is it has an addition, it has a scalar multiplication, it it has a multiplication, it has a subtraction, it has a 0, it has a 1, and it has a bunch of equations. And then it's a set. So that's all hiding under that. And we can prove, because this is effectively the elimination principle for this higher inductive type, that it satisfies the universal property we expect, which is that to take a map, an R algebra map out of this, we just restrict it to the variables. So this gives a straightforward definition of Rx. We just say it's a free R algebra generated by a single element, which we call X.
And could you please go back to the
Yes, please.
So you're saying that so A isn't okay, but so the type I is not truncated.
No, I isn't truncated, but because we're mapping into it, because we're forcing it to be a set,
So it doesn't matter.
it will generate the same thing as its set truncation does. So we get our definition of Rx. Oops, sorry. It's a sneak peek. So, but it's not really clear how to define the degree out of this. And the reason is that you look at this definition, to map out of the higher inductive type, effectively what you do is you take the thing you were defining and you stick in the thing you're trying to map into, and then you try to witness terms in all of those types. That's a vague way of putting it. In other words, really it's very helpful to map out of this when if you're trying to map out of the free algebra into an algebra. But the upper naturals are not going to be an algebra. So it's not clear. So we can do a new definition, and this one's more logical. It feels more like constructing something in set theory. We just define the polynomials to be the type of eventually vanishing sequences. So we define it to be an eventually vanishing sequence of coefficients, where eventually vanishing means this one. So then we can really easily define the degree, because it's sort of right there. We can prove that this has the expected universal property. And I'll just tell you about that really quick, because it's kind of cute. So I'll do it over here. So R X S into A, an algebra. How does this work? Well, I should tell you X here. What X means is the sequence that begins with 0, then has a 1, then the rest of it's 0. So in other words, the coefficient of X is 1. So to map out of this, we're going to be mapping out of this type, and that exists here is hiding a propositional truncation. So what we're going to use is the universal property of the propositional truncation. Now, luckily, we're mapping into a set, so there's not much work. It's actually just basically how it works in classical mathematics, which is we can say that, oh, okay, so there exists an n, so let me have it. And then we write down the function. So if we have f here, then there exists an n, after which it is going to be 0. So we map it to the sum of its coefficients like this, forming it with x. I'm sorry. A. So given an element A, we're proving this sort of adjunction here. We map it like this, except now we are mapping out of a proposition, so we have to make sure this is well defined, which means invariant under our choice of n. So this is this. So if n prime also witnessed f eventually vanishing, then without lots of generality, one of the two is bigger. And everything in between there is 0. So then, we know that the sum up to n prime of fi xi or fi ai equals the sum of the n of fi. So that's how that works, which I think is kind of cute. So next we can define the degree. The degree is just going to be the proposition that after this point, all our coefficients vanish. We can prove some basic facts. So if your degree is a bona fide natural number, then your polynomial is a bona fide polynomial, bona fide sum of its coefficients, which is great. And then we have 2 facts that you might expect, maybe with fewer less than or equal to's, but I'm doing this for a fully general ring, so there you go. And these are just sort of straightforward. You just check. Now, I also wanted this fact about composition. This is sort of like how I ended up here. I was trying to say some arguments about how if you have an algebraic extension of the affine line, you know that there is sort of nearly a polynomial on which everything vanishes. And I was trying to do some things about the composites of polynomials to show something. So this is actually where I ended up. And I had to unwind myself back all the way to figure out what it meant to take a degree. So what about this? The answer is you could write down what the composite does on coefficients, but I'm too lazy for that. So I'm just going to define a whole new natural number. I mean, a whole new polynomial ring. So we take this observation, which is, I suppose it's due to Horner, that a polynomial can be written like this. You know, and Horner goes, this is a great way to represent polynomials. We can write it in this normal form. But any polynomial, by expanding this process out, we get a way of writing it. And we can turn that into a higher inductive definition. So we construct our polynomial by including constants, and then giving this constructor, which is the Horner normal form constructor, and then we just have to add an equation to make sure that if we multiplied x by 0, it's not there anymore. And then we have to force it to be a set, just to make sure we don't have too many extra equations lying around. And we can prove this also has a correct universal property. And at this point, I'll just mention that because they all have the same universal property, all of these three polynomials are equivalent by the function that sends x in one to x in the other. So they're really going to work exactly the same. And now here we can define the composite by induction on the polynomial. So we define it like this. We say that if our polynomial is constant, then composite is constant. And if we have it in some form like this, then we just plug in the other polynomial for x. And then we check, so this is mapping out of a higher inductive type, so we have to check that it satisfies this equality. We check that this works. Pretty straightforward, do the defining equation, and then we just realize we're mapping into a set. Cool. So we can now prove that for any polynomials, we have this inequality here, and we do it by using the induction on Horner normal form. So if it's constant, it just works. And so in the inductive step here, we take the Horner normal form, we can plug it in, we can take off that adding a constant, because adding a constant doesn't change degree. Then we can use the fact we already proved about products to break it up into a sum. And then we can use the inductive hypothesis to recurse. And then we do a little fun step here, which is distributivity. That's a big convolution thing. And then we realize that this adding 1 to our degree is the same as multiplying it by x. So it's a very straightforward, but if you don't do it this carefully, you can say wrong things, I'll say. So is my experience. So the slogan here is that instead of inducting on the degree, induct on the polynomial. And so my touchstone in this, as I was getting into this, is Lombardi and Kite is a 1,000-page book on constructive algebra, which is beautiful. And they induct on the degree. And I couldn't induct on the degree because my degrees weren't landing in the natural numbers. So I was like, oh no, what am I going to do? And then I realized that all their proofs when they induct on degree are in fact inducting on the Horner normal form. So it's really nice. And yeah, so I'll say some more about that. I'll say it right now. Basically, we can define the dimension of the vector space in the sort of obvious way. We can say that it's the minimum n such that it is isomorphic to Kn, and yes, this is equivalent to the minimum n such that it has a cardinality n basis using the other definition of cardinality. And we can prove, our sort of expected fact here. And again, I got into this because I was trying to do a little bit about algebraic extensions. Yeah, so now I'm going to turn to Crispness. But before I do, I want to mention that Lombardi and Kite and also Coquan developed a constructive theory of curl dimension, which I'm not going to go into because the definition is very interesting, but It's a bit long for me right now. And it is also defined by its upper bound, so it lands in the upper naturals, and then so those theories work as well. So you could define, for example, the dimension of a module as the curl dimension constructively of the ring mod D. So the theory continues to work, and that would give you a theory of dimension for spaces internally to say that the risky. The crispness. Finally, I'm going to say that we can get back to natural numbers as long as we didn't work continuously. So the way we don't work continuously is to change our type theory to allow ourselves to quantify discontinuously over variables. So this is formally done by Mike Schulman's cohesive homotopy type theory, where he, or spatial type theory generally, where he has a crisp term and so crisp variables, which are meant to be discontinuous, and the term is called crisp if all its free variables are crisp. And crisp variables must have crisp type, and you can only substitute crisp things in for crisp things. So if you're a type theorist, this is that, you know, the dependency goes backwards in the context. Right? So we think of a crisp point as a variable that's discontinuous, or a discontinuous point. So we add an axiom, a classicality axiom, which says that discontinuously every proposition is either true or false. And now I'll tell you about the extended natural numbers. Oh, if x is a crisp type, then we write flat x for the type of its crisp elements. So this is the final type theory. So the extended naturals is the type of monotone functions from the naturals to the Booleans. This intuitively should be a bit more discrete, but it turns out actually in constructive settings more generally, even in settings where you have flat and sharp, this is not discrete. In fact, this is the one-point compactification of the naturals, not assuming certain other constructive principles. So, for example, a model of spatial type theory with just flat and sharp is Johnstone's topological topos. And here, an infinity is the actual one-point compactification of the naturals, which is that the site of that topos is the endomorphisms of the one-point compactification of the naturals externally. And this is the Oneida. So equivalently, it's the type of upward closed decidable propositions. And so the extended naturals embed into the upper naturals by pushing forward the rule of the prop. And they're also a nice fact about them, because we have the decidable well-ordering principle. Every bounded upper natural is a natural. So they are, the bounded upper naturals are equivalent to the naturals. And finally, we can prove that the points of the upper naturals are the points of the extended naturals, and this restricts the boundedness, so that the points of the bounded upper naturals are the naturals. And finally, I'll mention that if we add a slightly stronger, less classical axiom, which does not follow immediately from the law of excluded middle, and does not hold in, for example, the topological topos, which is the countable axiom, the crisp countable axiom of choice, which says that if we have a crisp family of types varying over the natural number, and we have a merely have something in them for all n crisply, then we merely have a actual choice family of this actual sequence. And so assuming this, we know that the points of the extended naturals are just the naturals union infinity, and that actually shouldn't be, shouldn't just be points. We actually know that the extended naturals are equivalent to that type 2, using one extra slightly stronger fact about cohesion. There's a slight technical thing in there, which is that with a certain extra assumption, all propositions become discrete. So yeah, as a corollary, we have that everything I talked about here, if it's crisp, it's what you expected it to be. And that's the punchline. So if you have a crisp vector space, which you often do, but not always, then it has a natural number. It's finite dimensional. And Yeah, so one thing I might say is that the dimension I've mentioned here is the dimension that Hartshorne writes down if you do it in the little Zariski topos of sheaves. So that at least in that case it's the same thing. But I don't actually know what these upper naturals are in the big topuses.
A dimension of what? Sorry.
There it is. The dimension of a vector space.
Oh, of a vector
This
space.
actually gives that previous formula for, which is the standard formula for the dimension of a coherent sheet.
Okay. So, yeah.
Which
Good.
becomes internally becomes a vector space in the box. And I think that's it.
Can you drop the set condition for the free algebra? So do you get something which might be the correct thing without truncating to sets?
Yeah, I tried doing what we might call extremely naive derived geometry by just not putting in the truncation condition, and I didn't get anywhere with it. But you can do some things wildly without any coherence, and then it just if you have multiple structures involved, you end up wishing to put some extreme qualities in there. Yeah.
There was this question about IC figure. Some of you had your email or something. I don't know where this you wanted to take a ring and then add generically a free variable and do like a free geometry in the set. Yeah, I think it didn't really work for him because of also issues related with the degree. Now, maybe it's something that I'm interested in. Yeah.
Quick present. We have until 3:30, so let's give it until 3:30. We have 40 minutes. And then Felix will